to agree to be recorded, please say yes so that we can then put this up on YouTube later. But welcome everybody to the first of the online YCCSA seminar series. It's a little bit experimental to start with, and so to start with, what we've decided to do is have three members of YCCSA give lightning talks on what they've been up to during the pandemic, research-wise that is. And in the normal way, if what we'll do is have the presentation, maybe a couple of quick questions after the presentation, but then we'll have a big question and answer session after everybody has spoken, because there might be questions that link the various presentations together. Okay. So our first speaker is Professor Richard Law from the Maths and Biology department, who's going to be talking to us about fishing. I know during a lot of the pandemic, he was actually in New Zealand, and we were very jealous of him because he wasn't quite as locked down as the rest of us, but he has now returns to the UK and is going to tell us about his adventures with fishing for biodiversity. So would you like to share your screen, Richard?
Okay, right. So this is a new experience for me. I've never done one of these before, so you'll just have to bear with me when I get this wrong. Right. So let's presentation mode. Right. So can you see that all right? Is that coming? Okay, right. Well, yes, Susan wants to know what I was doing in New Zealand last year. So this is what I was doing. I was lucky enough to be marooned in New Zealand for a good long time. I arrived just as the world was closing down, so the middle of March, and there were no flights back to the UK as I could find until sometime in August. So I had much longer there, and actually was a great privilege because I went through their lockdown period and could see the kind of synergy of good governance and compliance of the population. So in a period of about, I suppose, well, less than 2 months, probably about 6 weeks, they brought the COVID outbreak. Well, they essentially eliminated the coronavirus from New Zealand, and the R value during this period, I think, was down at about 0.4. So I mean, it's quite extraordinary, the success of this, and points out that in the right circumstances or right conditions, you can actually keep this thing very well under control. Anyway, so by the time we got into June, so this being the New Zealand winter, we were out up in the mountains, and so if you know this part of the world, this is the Southern Alps up from Lake Tekapo at an absolutely glorious conditions, guided through these places by Rachel Binney, who's a researcher there. If you haven't been to New Zealand, you should definitely go. It's a brilliant place. Apart from that, I was working on what I take to be one of the big dilemmas we face in marine ecosystems, which is how to reconcile the need for conservation with the need to take some food from the sea. And I was hosted there by Mike Plank in the University of Canterbury Maths and Statistics Department. Many thanks to Mike for making this all possible. The sort of dilemma is that we have two sorts of stakeholders in the marine realm. We have the people who are concerned about conservation of marine ecosystems and the damage to their structure and function that's taking place, loss of biodiversity. And they take a fairly holistic view of marine ecosystems, seeing them as complex systems with many complicated interactions occurring inside them. On the other side, you've got the fisheries stakeholders, who obviously are primarily concerned with the yields they can get from the sea and making profits. You know, they've often got mortgages on their boats, so they need to make money to survive. And they're interested in the state of particular stocks, that ones they can sell in the market, not really in the whole ecosystem. So actually, it is the case that the fisheries people are now supposed to be interested in the ecosystem consequences of their actions. The Convention on Biological Diversity, the Malawi Principle, I think number 5, states that the conservation of the ecosystem structure and functioning should be a priority target in their thinking. However, it's not obvious that that is always the case, I think, as of now. And actually, if you go back to when these ideas about the ecosystem approach to fishing were kind of coming into place, this is around the millennium. So there was a meeting in Reykjavik organized by the FAO of the United Nations to look at this. And towards the end of the report they wrote, they looked into the future to see what might be going to happen. So this was about, I suppose, about 15 years ago. Now, one paradigm says that actually the positions that the stakeholders take will become more extreme as time goes on. So the conflicts between them will become greater. And as a result of this, because there's a lot of public pressure for conservation of the marine realm, the fishing people are likely to lose quite a lot of their fishing grounds as conservation becomes more important. So on the right here, on this thing, I've just pulled out a picture of where we're going with fishing boats at the moment. This is what's called a super trawler. It's a massive boat that can go all around the world and take out vast quantities of fish at a time from the sea. And the picture on the top there is the response of Greenpeace to these trawlers in the North Sea. So this was actually a Greenpeace boat out last autumn, and it was dropping 6-ton granite boulders onto the Dogger Bank. I suppose our thought is that even if you've got a super trawler, if you get one of these in your net, you're probably going to get your net destroyed. So you probably don't want to go fishing there. Interestingly, the way they were actually putting these boulders down was in a marine protected area. So you might think they wouldn't have been fishing there anyway, but actually there are marine protected areas where fishermen are allowed to fish. So that seems surprising, but it happens to be true. So there you've got the kind of the collision of the stakeholders happening. And that was one of the paradigms that was being suggested back 15 years ago. The other thought was that actually you could go in another direction in which the stakeholders actually come closer together in their thinking. The ecosystem stakeholders, the conservationists, would need to accept that some fishing will have to take place. The coastal communities are often quite poor and they depend on fishing for food and income. Of course, fish are actually a very good source of food. I mean, from malnourished people, they provide a very good and healthy diet. The fisheries stakeholders on the other side need to accept that conservation of marine ecosystems is really important, and we do have to leave them as undamaged as possible for future generations. We need to properly embrace an ecosystem approach to management. The question is how do we actually do this? How can we bring these things together? How can we make fisheries go in the direction of more being concerned about the goals of conservation? I mean, this would seem to be in some ways an impossibility. But I like to think about impossible problems, so this is what I went off to New Zealand to do. So in answer to your question, what I was doing, Susan, I'd gone fishing, I have to say that it's easier to go fishing on a computer than I find to do it in reality. My success in fishing is rather better, and I can make up the rules and actually catch the fish on a computer. Without going into details here, this is an assemblage of 15 or so fish species with different maximum body sizes from about 500 grams up to about 20 kilos. And this is the biomass that they are roughly at equilibrium before any fishing actually starts. And there's of course quite a lot of stuff inside there, which I won't go into, but just to show you the sort of basic ideas. These models are concerned with the flow of mass, of biomass through the ecosystem. So things only grow by feeding on other things. They start off feeding down on the plankton, and then as they grow, they start to feed on larger things according to a kind of feeding kernel. They feed within species, on each other within species, but they also feed across species. So you've got a lot of interactions operating across the food web. They're not in the way that usually are thought of in food web models. And of course, they're dying for various reasons. Obviously, they die because when they're eaten, and they also die rather heavily when they're larvae. That's a rather vulnerable stage of life. There's some background death, and then there's obviously death from fishing as well. So those are the kind of processes built into a system of partial differential equations, which we can happily ignore for now. What happens when you do this? I'm just putting up a comparison here between two sorts of fishing. One is a kind of caricature of what we might be doing at the minute, where we put out roughly a constant fishing mortality across a range of different species. This is the 15 species, and they're being harvested here from about 500 grams onwards. At the start, we had the pristine ecosystem, and then over 50 years of fishing taking place. And you can see that in spite of the fact that mortalities are rather low here, the rate of fishing mortality is about 0.1 per year, which is, well, quite a bit lower than would normally be applied in reality. These rare species are on the way out. This is the biomass is going down. On the other side, the right-hand side, I've just made one small change actually to the fishing, which is to weight it by the production rate of the species themselves. Now, the rare species have got low production rates, and so the fishing mortalities are correspondingly small there. And as you can see, that's actually maintaining the biomass of the different species in the ecosystem remarkably well, and including the rare species that were being rather clobbered by the fishing of the other kinds. So here is a way in which you can, in principle, fish to maintain the biodiversity inside the ecosystem. How does this actually work? Well, this is the comparison still between two sorts of fishing: constant fishing mortality rate on the left-hand side, and the corresponding fall in the reduction of the biomass of these large rare species. But this other approach is actually the fishing mortalities are much lower on these big endangered species, but also the fishing mortality is responding to their changes in production rates. So these ones here, in which the biomass has gone down over this period of time, the fishing mortality, you can see the open circles are what they were at the beginning of the 50-year period, and the black circles are what they are at the end of the 50-year period. They're actually going down. They're responding to the fact that that the biomass has gone down, so they're actually fishing less hard on those ones. And conversely, there's one which has actually gone up here, and the fishing mortality has gone up over the course of time. So there's a kind of feedback operating in these systems which will help to maintain the populations there. Perhaps one of the intriguing things about this is to do with a quantity that in fisheries science we're quite interested in, which is the exploitation ratios, which is the ratio of the yield taken, say, per year, and the production over that same period of time. You might think, I mean, it's fairly intuitive that actually if you keep that ratio fairly small, then all should be well. actually. So still keeping the same comparison, the fishing mortality rates on the left-hand side, the constant, and the exploitation ratio is sitting at about 0.25. Now, in fisheries, there's a sort of rule of thumb that says if you keep the exploitation rates below about 0.5, then all should be okay. But actually, even down at 0.25, we could see that previously there's some species are collapsing. And I've actually put a trajectory of one of them onto here. So this species started off at the beginning here, and it's just moving down this line as time goes on. So even having a constant but fairly low exploitation ratio is not enough to save these rare species. In contrast, if you go to the other one where we're fishing but allowing for the production rates, it's actually this relationship between the yield and production is scaling quite differently. The species that are rare have much lower yields relative to the production than these other ones. So this different scaling is something that I don't think is recognized in fisheries, and the need for it is not recognized. But actually, that is where you need to go if you want to protect the rare species. At the minute, operating on the basis of a constant exploitation ratio, we're actually running the risk of driving the biodiversity in these systems down. I guess that's about my slot, isn't it? So just summing up, it's clear to me, at least, that you can fish for biodiversity. You can fish to better maintain the ecosystem structure and function. You can bring conservation and fisheries into a better alignment. However, to do this, you actually need a kind of paradigm shift. I mean, the rare species are going to need much more protection than they get now. As Susan is recording this, I better put in a disclaimer here, which is that, I mean, such far-reaching conclusions on the basis of a 10-minute talk are, of course, totally unjustified. You have to kind of read the small print to understand this better. Okay, right.
Okay, thanks very much, Richard. Are there one or two quick questions before we move to the next talk, which I'm going to ask Matt to go next, if that's okay. If you want to raise your hand in the chat, however that works. Right, nobody's asking a question. So Richard, if you could stop sharing and Matt could start sharing. So
yeah, you see it.
Excellent. Okay, thanks. So our second speaker is Dr. Matt Dale from computer science. Obviously, all these people are also members of ICSA who's speaking today, but computer science, who is an RA on our current EPSRC project called Spinspired, doing some really fascinating stuff with reservoir computers and magnetic films, and he's just going to give us a quick overview of that today. So take it away, Matt.
Okay. So you might have heard some of my stuff before. Some of this is carrying on. So I'm interested in magnetic devices because of some of their properties, which are much better than some of the old systems that I've used. But I'll go through this stuff for you. So a general overview of reservoir computing, just so everyone knows what I'm talking about. So it's a brain-inspired model. And the idea is to harness this, the nonlinear dynamics going on, and the oscillation and the kind of activities, kind of macroscopic activities going on. And you exploit these to perform different things in machine learning, different computing problems, etc. So it's a kind of example of what a reservoir computer is. typical one is a random network of nonlinear nodes. This was early on a recurrent neural network, which had these feedback connections. And these feedback connections enabled you to basically have memory, and you can make relations in time. So what a reservoir does, this bit in the middle, so it projects the input that goes into it into a high dimensional space. And this enables you to essentially do what's going on here, is you have an input, it projects it into this high dimensional space, which you can basically put a hyperplane between, and you can split data points, so you can extract features linearly. And that's kind of what's going on in the center of this reservoir here. So the extraction bit's done at this readout, which is just linear. So these reservoirs themselves, as I said, had feedback connections. This allows you to have temporal relationships. The really interesting tasks that we want usually involve time. That's why we're interested in this model. And a thing to note about these reservoirs is that this projection is really expensive to compute on conventional systems. So it might be large matrices, multiplications. So what we are doing here is we want to find a system that can essentially do this projection for free, a system that does it naturally, and also has this fading memory inside of it. So arguably a lot of physical systems do this. And we're going to look at magnetic systems. So the proposed system that we looked at was a ferromagnetic film. So replace this reservoir with this layout of a magnetic film here that's split into into cells. So this is actually a simulation of a film, a micromagnetic simulation of a film. So inside is a collection of atoms, and then you get the averaging of this magnetic moment happening within the film, which gives you a direction, and each one of these has a different direction depending on alignment and activity. So if one cell moves, it is coupled to these other cells, which moves them in different directions, etc. And then so you could input a signal. So say you input a spike into the center of it, you get this kind of spiking behavior, and then you get the coupling happening between all of them. And it kind of looks something like this. So you inject your input, and you can see you've got these essentially like these waveforms spreading out. And if you add more of them, they interact with each other, etc. And this is the dynamics, this nonlinear dynamics that we're exploiting here to solve these computing problems. So once you came up with this system, I wanted to test them on some benchmark tasks in machine learning. So as I mentioned, we're interested in these temporal problems. Just a selection of these problems were predicting time series. One was predicting a chaotic laser. So you give it a laser, you try to predict one or a few time steps in the future. And the second task we were looking at was this basically this nonlinear system, which you could introduce extra time lags in, so you could test how much memory the system had. So before I get onto this, I'll just explain what we wanted to do with these materials is compare them against the state of the art, let's say the digital reservoirs that exist. What we used is we used 3 different materials. So we used nickel, cobalt, and iron, and we used them at different sizes. So all the orange ones here are the films. The green ones are these recurrent neural networks where you can basically have a connection to any other node within the connection, and the graph ones is a more restricted topology. So it's just a lattice of nodes. So there's no looping around from one edge to the other edge, anything like that going on. And the argument here is that acts more like these films do, rather than these long distance connections. So as we go along the columns, we've got the 3 different sizes, and as we go in rows, we've got the different tasks. So the main thing here is at smaller sizes, we're seeing that the materials perform better than or as good as the best known state-of-the-art systems. As you can imagine, if these are small thin films, they're doing this much more efficiently, power efficiently, smaller space and everything compared to a desktop computer that's having to run these algorithms, these digital reservoirs. So as size increases, depending on the task, we get different things, but generally we're kind of with similar performances with the restricted one and the unrestricted one. And the harder task, so this NOMA 10, it requires more memory. It requires you to remember 10 time steps in the past. We see that performance lags a little bit behind, but it's not too far behind the best state-of-the-art systems. And then we've got the harder problem, which is the NOMA 30, which requires longer memory, 30 time steps. We really start to see a difference between the materials here, and we can see that some materials have a bigger memory, or we can guess that they have a bigger memory. So Cobalt looks like it has a bigger memory because it's able to perform the task, and compared to the other two that look like they have a lower memory. So ultimately, what we see here is that they're very similar to the best ones. So just to show you basically what's going on here, if I go back to the previous image, we've got this input layer, got the reservoir, and we've got the output. So this is what I'm about to show you. So this is my input layer. This is where the different inputs are going into the film. This is the states of what's going on in the film, and this is the output of it. So we've got a little video. So this is just probing it at different time steps. You can see this undulating, moving film, and it has some output weights that extracts these states and puts them into this final signal. So we have a desired output and our actual output. So play it again. Oh, I'll play the other. So the desired output and actual output, and you see with time it's doing a very close matching. So we can see that although we might not understand exactly what's going on in here, we're seeing that it's actually solving the problem. So what we wanted to look at was a bit more into this dynamics. We wanted to see, how much memory it had, how nonlinear the system was. So what we did is got those top results, and we plotted them with these metrics. So they're measuring, as I said, the nonlinearity in short-term memory. So we have the kernel rank, which is on the bottom, and the short-term on the y-axis. And we can see for each of the tasks, they kind of cluster in certain positions, independent of what the material is. So this is a good indicator of what kind of dynamics the task requires. So just as a brief explanation, this one's fairly non-linear problem, the laser one, but it doesn't require much memory. And you can see this is consistent along here. And then as we go up to the NOMA 10 and NOMA 30, we see that it requires more memory, but it's not as non-linear. And if we get to the 30, we see it requires a lot more memory. And we can actually see that the Cobalt is able to have a larger memory than the other ones do, and that kind of goes back and explains why it performs better than the other ones. So we just did some other tests, basically, to look at, how could you physically make these materials. We had a little layout of saying this is how you would construct such a system. I don't think we know the full details of actually how to do it, but maybe we'll spur someone to make it. So you have these local magnetic sources, and you have these, I don't like saying that word, sensors on the top. And so it's just looking at the local magnetic fields on the film. What we wanted to look at was scaling. So this is an important thing. If you want to continue to build these systems, you want to see that they actually scale. What we found is that they scale fairly well, don't scale as good as the digital systems, and there's probably reasons for that. And we think some of that might be down to things like edge effects happening. So the bigger you film, the further your edges are away from each other. So it's possibly that's a thing that was being exploited but isn't being exploited as much now. So there needs to be more investigation onto this. But in general, they scale very, very well compared to the digital systems. And our initial experiments were looking at very thin films and low temperatures, just to ignore basically thermal noise. But if you really want to make these systems, that's going to be a problem. So we wanted to see these effects. So we just did some plots of changing the film thickness and changing the temperature. Ideally, we want to be at room temperature. As you can see, so the lighter color is the error in the performance. The error on the task is worse. Green is better. You see that as temperature increases, performance goes down. It was kind of to be expected. And these films like being very thin. There's possibly ways to get around this. There's little techniques you can use in building this that will aid you to get higher temperatures and probably thicker films, but we didn't explore that. So basically, in conclusion, we showed that the material is performing this nonlinear projection and has a fading memory because it's able to perform these tasks. What we actually have used is very different from a recurrent neural network, as we don't have any discrete units. It's a film. It's and what we're doing is we're just locally observing points in it. This is a nice, interesting thing because it means you could potentially reduce the size of these kind of neuromorphic devices because you can have much smaller films. Because maybe each device is the same size as one of these films. So the system currently operates very fast because it's exploiting these the magnetic dynamics happening very fast. It doesn't require additional processing that some other systems do provide. And ideally, this platform could enable us to explore very different materials as well. So ones that we haven't looked at, but are interesting, promising ones that have different advantages. So it can go to faster speeds, it might be more power efficient, etc. And yeah, basically with this, there's a potential for new, faster, energy efficient devices that we could embed in kind of mobile applications, if you want. But yeah, that's me.
Thanks very much, Matt. Are there any quick questions before we move on to our final speaker? I mean, there's time for lots of questions afterwards, but I don't see any hands going up in the participants thing, so I'm either missing how this works or whatever. So Phil, could you come on next, please? Great, so thanks. So our third speaker, lightning speaker from ICSA, is Garnett, who's got an interesting background of biology, computer science, and management in the best traditions of ICSA, having done lots of different things. And today he's going to talk to us about cybernetics and the control of the intelligent organization, which sounds quite frightening, actually. Over to you, Phil.
Hi, everyone. So this is a sort of a mixture of both old and new in a way. So I've got quite interested in two things really. One is the sort of broad idea of thinking about organizations as complex systems and what that means for how they're organized and run and how they do the work that they're intended to do. But within that, the role of technology, I think, is quite interesting because there's a growing interest in things like AI and machine learning type technologies that are kind of getting into this space. And I think that raises two issues. One is what's the future of the organization and how decisions and things are made within organizations, including how they're managed, when that future might include increasingly advanced AIs and things. But also there's a sort of more immediate concern around the way these technologies are marketed today, which I think is quite interesting. So I kind of want to talk a little bit about those because they overlap with some of my interests that I've been thinking about during the pandemic, but also before. And it also links a little bit with the talk I did quite some time ago about kind of systemic decision making in organizations and where those decisions originate from, which I think is quite interesting. So I'm going to talk a little bit today about how cybernetics is a useful theoretical lens to help us approach this problem, I think. So I'll hopefully make that case a little bit at the start, and then I'm going to have a bit of fun showing you some AI tools that you can buy for your organization that I think you'll find some interesting, some funny, and some really disturbing. So that's the idea. So I think I've probably done this slide, so I'll move on. So cybernetics, it's possible that some of you don't know much about cybernetics. It's got a long history. It came from, well, this chap, Norbert Wiener, was one of the kind of founding thinkers in this area, and he described it as control and communication in the animal and the machine. And I believe this is correct, that this story, this started while they were essentially kind of exiled from the war in Mexico, I think. And the discussion was, we need a discipline of control to understand how things are controlled. And they spoke mostly about weapons of war at the time. And I think the most famous example was anti-aircraft guns. And it was about how in operating an anti-aircraft gun, it really raises some interesting questions about how much of a part of you that machine becomes, basically. But you may also have seen things like this, which is the idea of where the controller fits in the system and whether or not that controller is part of a feedback process. So these are, when I'm doing my Cybernetics 101 for students, this is the kind of thing I get them to think about. So there's a sort of traditional view that a controller of the system might sit outside it and they sort of pull levers and they're sort of remote from the system they're controlling. Although there might be feedback processes and so on within the system itself. But second order cybernetics, which I think is probably more popular now, certainly, and probably better really in general, is to think actually you're part of that system. So even if you're a controller in a control room somewhere, you're actually embedded in that system, you're part of it. And the fact that you're there changes the way that system behaves. So you're embedded in a feedback system with the rest of that larger system as well. So if you think back to that example of the anti-aircraft gun, you're sort of, the boundary between you and the machine is not entirely clear. So to put that a little bit more in the context of today's kind of technologies, if you think about you and your phone, or your computer, you could rightly ask the question of, well, where does you end and that computer begin? And I think that we've probably all felt that it's like that at times with technology. Like if you suddenly lose a lot of data or whatever, it's like you've lost part of your own mind. So I think organizations are quite similar. So that's my argument with why cybernetics is a useful theoretical framework to investigate this within organizations, is not only is where's the boundary between you and the larger organization as an individual, but also you, that organization, and the technology within it, I think is a similar kind of issue. So it raises similar questions. And then the last thing I've got at the bottom here is who or what is making the decisions. And you could perhaps argue that it's the organization that's making the decisions. It's not a single actor or a single piece of technology within it that's making the decisions. And that is a kind of link back to the previous talk I did in real life, where we were talking about kind of systemic decision-making processes that are not always particularly good. So, okay, so now we'll move on to sort of introducing these AI tools. I just wanted to highlight a couple of things about them. Organizations are spending much more money in buying all kinds of tools that are called AI, which I think is perhaps a bit of a stretch, to say the least. Machine learning might be more accurate, but just analytical tools is perhaps the safest thing to call them at the minute, I would say. But they are establishing this idea that AI tools exist in organizations and they're part of your everyday experience of those organizations. Maybe not us, although learning analytics would be the example I would point to in the case of universities. But keep in mind that there seems to be a push to normalize the presence of AI in certain types of work, which I think is interesting. And the analysis they do is frequently passive. So it fits around your normal working life. It's not evident, it's not right in your face. And I would say that's perhaps deliberate. So if you put something in the background and it becomes part of the environment, you're less likely to question it. And then as its capacity changes, as the technology develops, then actually that could be qualitatively quite a different thing. So again, that links back to why I think cybernetics is a useful tool to kind of critique this emerging presence of this sort of technology. So what do they look like? This is the fun bit. So I've got loads of these, so actually we'll probably run out of time, I would imagine, but we'll see how far we get. So they take on different characters in different contexts. One of the common ones is sort of internal threat detection tools, or even external and internal threat detection tools. So the idea is, and this is their sort of language, is they detect and eliminate all forms of threat on your network. And they often use quite interesting biological metaphors here, like artificial immune systems. So it's an artificial immune system for the organization, which does sort of suggest they believe it has the capacity to differentiate self from non-self. So what should be there in the organization versus what shouldn't, and therefore should be eliminated, which I think is quite provocative a language, to be honest. And there's a quote here from the Department of Energy. This is the US Department of Energy. General Electric scientists plan to develop advanced cyber detection and immune system technologies that aim to halt attacks on critical power infrastructures. So that's one way this is appearing, as this sort of background constant analysis that can tell you whether or not there's been an invasion of non-self into your organization. And actually, I should say, I think I've got, yeah, I'll come back to it actually, but I've mixed in my slides a bit here. So just park that and keep it in mind. The other area where we see this, which is more of a kind of management domain, which I think is quite interesting, is the sort of algorithmic management of people. And the most obvious example is things like the gig economy. And here, your entire working day is automated by algorithms that are supposedly like AIs, but not really. But that's the sort of narrative that's often presented. And I think you can legitimately ask, well, who is the manager in that context? And also, what is the role of the person? You could say that it's sort of dehumanizing the person in a way, because they become more of the machine in this cybernetic system, and there isn't really a human present anymore, because the person who is the gig worker just gets told what to do by an algorithm that they can't argue with and can never meet or have a discussion with. And that algorithm will assign them work based on their previous performance alone, and not really worry too much about whether they're ill or having a bad day or whatever. And we're starting to see some organization against this within the gig worker communities through things like unionization and so on. If you're interested, and obviously it's a massive form of workplace surveillance, which all of these tools have components of. This is perhaps the most visible. There's a paper here that's quite good by Gemma Newlands that came out last year, I think. But to go back, so I mixed my order up a bit, but never mind. To switch back into that kind of internal threat detection thing, there's another technology called dark trace. They always have brilliant names, these. I think that there's obviously some, I think they betray a lot of their thinking in the naming of things. And actually in a paper I'm writing, I talk a bit about how important it is that we name things in certain ways. I think dark trace is a very good example. So again, modeled on the human immune system, dark trace's technology is the world-leading enterprise-grade AI with thousands of customers. They do have lots of customers, actually. Organizations like BT use dark trace. Ground truths, everything attached to the network, including people. So that was the additional thing that I wanted to mention, was the internal threats include the employees. So you are potentially a threat. And your status of whether or not you are threatening is based on the distance you depart from your original ground truth. So to explain that in a different way, when you join the network, the system benchmarks your behavior and then cross-references that against similar kinds of employees, but then continuously checks your behavior against your past behavior. And if it changes, it can then flag you as potentially threatening because your behaviors become anomalous, basically. So if you deviate by some arbitrary threshold, you might become a threat. They have lots of stories about how they kind of detect kettles that are spying on people and stuff like that. But there's stories about how they know then people have, got pregnant or something because their behavior in the workplace changes. Okay, so I think I'm pretty much out of time, but I wanted to show one more. So this is another one that produced by a company called Keen Corp. And this is like corporate welfare. So this is monitoring staff for well-being. And this picture is hilarious. So these lines of connection go between machines and then the hearts of the people in the picture. So you're connected by your hearts with your laptop and each other and your phone and whatever. So I think that's just kind of funny, but I think underlying this, it's the same kind of thing, right? It's continuous monitoring of people. In this case, it's for, it's for the supposedly group welfare and effectiveness, but actually there's always this more sinister aspect to it as well. So I think that's kind of it. There's another one, sentiment analysis for teams. This actually is now illegal under GDPR, which is quite nice, but they're finding ways around it. Palantir, yeah, you've probably all seen the famous orb. They're huge players in this space as well. And in fact, they do everything from mass detection of terrorists to similar kinds of tools embedded in organizations. And Palantir, if you didn't know, which is the name of the company, is the seeing stones in the Lord of the Rings, which allow you to see everything that's happening in the Middle Earth, basically. So, yeah. Oh yeah, learning analytics in universities is the same kind of thing. And they're embedding it into children's toys just to make sure that we're all completely on board with this by the time you grow up. So to conclude quite quickly, I think cybernetics is a useful framework to help us both understand how these technologies will change organizations and the management as a sort of discipline and act, the act of managing people. But in the shorter term, I think we also need a really effective way of critiquing these tools and their use and the claims that are made about them, because as you can see, there's some quite sinister sides to a lot of this stuff. Okay, so sorry, I've gone over my time, but I'll stop there.
That's okay. Thanks very much, Phil. Okay, so we're now moving from the presentation part to the Q&A session. So if people, please do feel free to switch your cameras on. I'm in two minds about whether to continue recording the Q&A or not, and that's up to people. Maybe, I don't know if we can have a vote. Can people put their thumbs up if they're happy with the Q&A being recorded? There's some nodding going on. You can put thumbs up, you know, put lots of, okay, there seems to be a rough consensus. Oh, Richard put his thumb down.
I think after discussing AI and tracking and maybe.
Okay. Well, I mean that's a valid point. Okay. I will, in that case, I think that is a valid point. So I will stop the recording at that point. Now, I do completely agree. That was why I myself was in two minds about it, whether or not to do that. So I will actually stop recording at this point. And people who are watching it later, you're missing the wonderful discussion that's coming next. Okay, so come along to the next ones for real. So I have, do I want to stop recording?